you very much for having me. Given the backgrounds here, I feel like I almost should have talked about what I did 10 years ago, because that was about agent-based modeling in suburban systems. Specifically, we looked at suburban sprawl. I was affiliated with a group that Dan Brown was the PI on at the University of Michigan. And so I actually did throw in a slide at the very end to talk a little bit about that work, so I'll get to you that at the very end. But a lot of the methods I'm going to mention I think were applicable in both domains. And so I have both a application area interest, which is right now it's among how humans interact and exchange large scales amounts of information. But I also have a methodology interest, which is the complex systems kind of approach method, which basically boils down to making sure that you're building your models at the individual level, at the level of the agent, or in some of the biological systems we've done in the past, at the level of the animal or the entity, even down to the level of the cell at times, right? And then looking at how those different individual level models interact to form aggregate patterns of behavior, emergent patterns of behavior that aren't really definable at the level of any of the individuals. So I'm going to talk a little bit about that at the end of the talk, but I wanted to kind of show you some of the most recent research that we've been doing in this area, specifically within the context of social media. And as Joseph mentioned, I do direct something called the Center for Complexity in Business. We're a small little center that's taken all these approaches and tried to understand business and management science. And most of the work I'm going to talk about today is a specific offshoot of the Center for Complexity called SM3, which is social media micromodeling. It's a NSF and DARPA funded project that we're doing to understand the exchange of information and influence on social media. So I always like to lead with a couple of questions that I plan to answer by the end of the talk, and maybe this keeps you around and interested so you can figure out how we get to these answers, right? And so the first question I am going to discuss is, who are the most influential people in social media? And the kind of punchline to this, the kind of gotcha, is that it's not always the person who has the most friends or the most followers on Twitter or whatever, that there are other rules of how people define influence. Another aspect I'm going to talk about is how is trust earned in social media. And in this particular context, I'm talking specifically about the fact that you can actually engineer trust, that you can actually create environments that are more likely to generate trust among individuals. And finally, and this might be very relevant to some of the contexts that you were interested in, is how does information diffuse in urgent situations? Most of the diffusion of information models basically don't assume that time is of the essence. And so what would happen if that is the case? And there's a question as to whether the social network actually matters in that space. So we're going to talk a little bit about that at the very end. So the influence work. So this is joint work with Forrest Stondahl, who is at Central College now, was a graduate student when we started this project, and Uri Walensky, who is at the at Northwestern University, and he was my postdoctoral advisor. The basic question here is, how do you measure? And this, in some ways, this also relates to some of these questions about understanding ecosystems and understanding a lot of other aspects of information and energy exchange, which are about how do you measure influence in these spaces? How do you determine who has the biggest connection? And a standard kind of rule of thumb that a lot of people look at is that you assume that the individual entity with the most connections is the most influential, that they have the biggest impact if you were to give them something to propagate or if you were to remove them from the system, right? And we wanted to kind of question that assumption. That assumption has been tested in some cases, but not in others. And so we wanted to test it in a particular context. And moreover, we wanted to be able to assess, can we place a value on an individual entity, right? An individual space within this overall system. And our fundamental assumption is if we can simulate a diffusion process, if we can simulate some sort of process occurring on this network at the micro level within a large-scale network system, then we can assess these kind of questions and we can try and understand these questions, right? So the particular scenario we're going to talk about is we're going to assume, because now I am a professor of marketing, so I have to spend some time talking about marketing. We're going to assume that you are a brand manager or an advocacy group manager or something like that, that you want to get a piece of information out to the public in some way, right? And you want to educate the public about your product or your idea or whatever you're trying to do, right? And you have some way, you have some amount of budget by which you can reach out to a certain number of people and kind of convince them that this is a good idea, right? You have some amount of effort you can do, right? So there are two questions we want to answer, right? Who should you reach out and how many people should you reach out? And the way we're going to assess different strategies, different answers to that is by calculating what we're going to call the net present value of the network. And the net present value of the network, quite simply, is that you look at how far into the future it takes till people adopt the idea or adopt the product or whatever, and you add up those time periods at the time at which they do, discounting for how far into the future it is, right? And so the standard idea is that, if someone buys a product worth $1 today from you, $1 tomorrow from you, then that would have been equivalent to them paying you 90 cents for that product today, right? And so you kind of continue this discount factor all the way out. It allows you to compare both rate and value of the product, of the diffusion of information over time, right? So you can ask the question, then which individuals should you seed to have the quickest and largest impact in this network, right? And as I mentioned, the standard rule of thumb, and this is actually done in college campuses, is that marketing managers will go into a college campus and kind of look to see who seems to have the most friends. They'll give them the newest iPad or the newest PlayStation 4, which just got announced, right? And try and encourage them to talk positively about it to their friends. And a lot of times these go under the names of brand ambassadors, or they have other clever ways of disguise the fact that they're actually just selling products. But that's the general idea, right? And so that's the standard rule of thumb. But you could imagine a couple of alternative strategies, right? So being from, as I mentioned, born in Ohio, being from the Midwestern part of the United States, I always take it back to the high school analogy when teaching this to my students, right? So in the Midwest, in high school, if you were to identify the person who had the most friends, it's almost inevitably the captain of the football team, right? So this strategy is essentially giving the product to the captains of the football team, right, or a few select members of the football team. Another strategy would be to seed people whose friends don't know each other, right? So let's imagine that, for instance, the goalie on the soccer team also has friends, also happens to play first chair violin in the band symphony, right? That's a very diverse set of individuals probably, right? And so as a result of that, that might actually cause a new adoption to spread quicker because it goes within these two different distinct groups of each other, right? Finally, you could imagine that there is actually someone that is close to the center of this overall network, right? If you were to take this network and spread it out, that there's someone who has the fewest possible steps to any other individual. And it might be someone who doesn't have a lot of friends and who has maybe a very high clustering coefficient. In other words, a lot of their friends know each other, right? So you could imagine, for instance, the librarian. She happens to have 4 friends, and somehow those 4 friends who all know each other, between that, know everybody in the entire high school very quickly, right? So that's kind of the idea, the different ways you could see these strategies. But you also might want to ask, how many people should you seed? How many people should you give the idea to? And the reason why this is important is because, obviously, the more people you give it to, the faster it's going to diffuse. But you almost inevitably cannibalize the very people who would be most likely to adopt by continuing to give more and more people more and more friends it. So for instance, let's say you seed a couple of the players of the football team, and then you immediately also give it to the linebackers or the running backs, right? Those people were also likely to adopt anyways because of the fact that the captains of the football team had it, right? So there's a cutoff point after which it becomes inefficient for you to continue to seed, right? But it's important to seed a lot because that means it will go quicker, right? The diffusion process will go quicker. So how many people should you seed? So before I do this, before I jump into the actual results, I always like to show a model. So this is the model this is actually a simplified version of the model that I have for demonstration purposes. But it's written in the NetLogo programming language, which is an agent-based modeling language that allows us to represent lots of different individuals in the space. And here we have a simple social network where we have 20 nodes connected through various ways, right? And what we can adjust over here is the strategy by which we're going to seed this network, right? So right now it's coded up so that it's seeding just the person who has the most friends in the network, right? So if we do that and we color the seed by rank, you can see that these red nodes are the individuals who are most likely to seed. Now this is also dependent upon the seeding fraction that we mentioned, right? Which of those nodes? So we can actually play out the scenario and see which individuals get seeded. So it's those 3. And then we can watch the diffusion process happen as it goes through the entire network until it reaches its maximum. Now we could try other, we could in fact try other strategies. So let's say instead of doing degree, we do 2-step. 2-step is the number of neighbors you have within 2 steps of your location. So it's degree plus the degree of your neighbors, right? And in fact, if you color C by ranks, you see we get some of the same individuals, but some of them have changed a little bit, right? And we could, in fact, look at that clustering coefficient, and this will actually be important. So the clustering coefficient is a measure of how many of your friends are also your friends, right? So it's a measure of the tightness of that particular node's local network, right? So as a result, these individuals who have no friends wind up not having a very low clustering coefficient. And in fact, and we think of that as a good thing because it means that their information will spread more widely. Now, in this particular case, they only have 1 friend. So that's actually not a good thing because it's not going to spread too widely because it only has the 1 connection. But this individual right here has a fairly low clustering coefficient, and this one does as well. And the reason why is because they're friends. Some of them know each other, but not all of them. Like specifically, that node doesn't know any of the other friends of this node, right? So we can also see what happens if we were to seed by that strategy. And of course, you see these individuals way out in the end, and that actually takes a lot longer. It's a stochastic simulation, but in general, it takes a lot longer than seeding just the high degree. But what we can also do is we can combine these 2 strategies. So in this case, I've set it so that we're seeding somewhat by degree and somewhat by clustering coefficient. And what you see now is that you get this emphasis on that particular node among others, and this node, which serves as a boundary between these 2 groups, right? And these groups, they're kind of working as what we sometimes refer to as boundary spanners in the space. And usually in this case, yeah, actually that one's, yeah, it adopted much quicker than it did for the other ones in this particular case. So that's the basic idea. Before I present the results, are there any questions about the basic concept, what we're looking at? Yeah.
So it seems to assume that the transmission between nodes is the same rate. And so what if you have individuals who are really communicative and others that don't?
It's a great question. In this particular case, we haven't looked at rate of communication. But in the next paper, the paper on trust I'll talk about, we actually have looked at what if, in fact, you were less likely to trust different pieces of communication, right? In fact, we did kind of look at rate because we used an empirical model of rate transmission in that case. So it's in there, but we didn't tease out how much of it was rate versus how much of it was trust in that particular example. But yeah, that's a great question. In fact, that's some of the work we're heading down to. And in fact, with the urgent diffusion case, that becomes even more important, right? Because now if you're interested in how likely am I to find out about, say, Hurricane Sandy heading into Manhattan, right, it becomes very important how often I'm on Twitter or not on Twitter, depending upon where I am in the world. Some places I might have heard about it regardless of whether or not I'm on Twitter at the time, right? And so that also plays into it, and we've started to build that into the urgent diffusion models. But it's not in this model. This model doesn't take that into account. Any other questions? OK. So here's the basic setup. We've got 5 networks. 4 of these are artificially generated. This is an Erdos-Renyi random graph. You just connect up a random number of individuals with a certain constant probability. It's basically included as a baseline. Not many people actually have a social network that looks like this, but you know, it's kind of the standard old assumption that you have just as likely a chance of interacting with anyone in the population, right? Then we have a lattice network, and a lattice network essentially means that a ring lattice in particular, every individual is connected uniformly to the same number of individuals on either side of them. This often is used as an example of something like a neighborhood, right? So if you think about people living in a neighborhood, something like conspicuous consumption often has this kind of a social network of effect, right? You see your friends adopt a particular car or mow their lawn, move to a particular company or whatever, or mow their lawn versus xeriscaping, and you kind of get the idea, you get that kind of spin over, right? Small world is interesting because it's kind of a combination of the two. So random has short average path lengths, right? Between any 2 nodes, it's very quick to get in this network. Lattice is very long average path lengths. It takes a long time for this node's information to reach that node's information, right? On the other hand, random has a low clustering coefficient. No one's friends know each other, right, in a random network. In a lattice network, everyone's friends know each other, right? So it's a highly clustered network, right? Small world takes the lattice network and randomly rewires a couple of the links. What that results in is a low average path length given a high clustering coefficient in the network, right? So it has a nice combination. Duncan Watts has a great paper among many, many, many other papers that have followed on that basically show this seems to be representative of a lot of the properties we see in real-world social networks. This is, in fact, the kind of network structure that gives rise to the 6 degrees of separation notion, among other things. There's also what's known as a preferential attachment network. So the problem with the small world representation is that it assumes everyone has roughly the same number of friends. That's not the case in any real-world social network that we've studied. In fact, there's an interesting contradiction. On average, your friends are likely to have more friends than you do, which comes out naturally because the number of friends people have in social networks is power law scaled. In other words, there's a lot of people who have very few number of friends and very few people who have lots and lots of friends. And this model basically represents that by saying that the probability of any individual attracting a new friend is proportional to the number of friends they already have, right? So individuals who have lots get more, and individuals who don't have any get less, right? That's the basic idea. That's also an artificial network. It's Barabasi and Albert, among others, and it's been shown to represent a lot of the real world, another set of properties of real world social networks we often observe. Finally, we used the one empirical, well, we actually used a second empirical study, but it was after the paper we published, that's drawn from Twitter, where we just extracted 1,000 nodes off of Twitter using a variety of sampling techniques. It turned out the results I'm going to present are pretty robust to the sampling method that we used by which we did this. So this is just a quick, if it works, visualization that one of my students put together of the forest put together. This is what happens when you have a PhD student in their last year and they take a graphics class. And so this shows the spread of one of the particular diffusions through the Twitter network. And besides just being eye candy, it actually has some important features. You can clearly see the different clusters that exist in the social network, and you can see that there are a few connections, but not many, between the different clusters in the space. And that's going to become somewhat important in some of the results that we're going to talk about. So the first question we'll answer is, how many people should you seed in this network, right? And that question, it turns out, has an interesting result. And essentially, what happens is that as you increase the inequality of the network, you need to seed fewer people, right? And this makes sense. And inequality in this case means the distribution over the number of friends you have, right? So if you have a network where all the friendship connections are concentrated in a very few number of individuals, then you just need to find those individuals, right? Because those are the ones who are going to spread your information widely. On the other hand, if you have a network where everybody looks roughly like everyone else in the network, then you need to seed the message very widely, because otherwise it's going to take a long time to percolate through the network. So specifically, we looked at the Gini coefficient, which is a measure of inequality of the network, where 0 means that everyone has exactly the same number of friends, and 1 means that one person has all the friends in the network. And we used that measure, and we show that it's roughly related to what we found to be the optimal seeding budget in this space. In other words, the value that maximized the net present value that we calculated. And it's related inversely. And so you can see that the random and lattice networks are up here, kind of need a high seeding budget, and they have a very equal distribution of the number of the friendships in the network. On the other hand, down here, you have the Twitter network, which has a very unequal distribution of friendship relations and yet requires a much lower seeding budget to achieve the same optimal value of net present value, right? So the general idea is that the more unequal the network, the less searching you need to do to find the people who are influential in that network.
So the optimal seeding budget is the number that have to be seeded to estimate information as quickly as possible.
Exactly. To maximize that net present value score that we talked about. But I should say it's also that number combined with a particular strategy. So for a particular strategy, there could be different optimal seeding budgets. What I'm presenting is the results for the maximum value for any strategy, any seeding budget combination that we found using the genetic algorithm. all told, we tried out about 1 million different hypotheses on all 5 different networks when you look at the actual how long it took the GA to run, right? And so we're pretty confident these are at least local optimal in the space.
Side, I mean, so one, if you look at web search and where, let's say, page rank or has starts with a set of C's and try to, have you looked at these?
So we deliberately didn't want to in this space. That's a great question. So doing some sort of page rank identification or doing an eigenvector analysis of what's going on in this space is something we had considered. We didn't do it because of the following argument. We wanted to make a paper, we wanted to look at a situation in which a marketing manager might actually have access to this data, right? And most brand managers don't have access to the full underlying social network. They only have access to the local properties of the network. Now, the average path link property I mentioned was a global property. You can't calculate that locally. But we basically threw that in because there was some other work that had shown had been important, and we wanted to see if, in fact, it mattered or not. And as you can see, as we'll show it didn't wind up mattering. So we seem to get good results with just local properties, right, that don't require something like a PageRank algorithm or hits algorithm or eigenvector, which requires global knowledge. Or, I mean, of course, there's local versions of all those, but really all of the properties we're talking about can be calculated with a 2-degree look around a focal node, which is kind of more likely the information you'll have in that space.
Follow-up question.
Yeah.
If you compare, let's suppose you assume you have global knowledge and you can compute a page rank or hits or eigenvector.
Yeah.
Have you compared them to?
So we haven't done it for hits or PageRank or any of those. And we did, I mean, the average path link was one of the things, and we specifically wanted to throw in one of them. At the time, we threw in that one just because there had been some discussion about it. And it turns out not to be useful in this particular case. But yes, that's something we've thought about doing, is looking at. There's actually a great paper by Eva Tardosh and John Kleinberg, and I'm trying to think of who the third author is, that basically shows that there is that this problem is NP complete in the hardest in the general case, but that you can use a greedy algorithm to get to a epsilon within the optimal solution. And one thought we've had is trying to build that and try to find out how close, but it turns out even the greedy algorithm is extremely computationally intensive, right? But looking at, so we hadn't really thought about doing it to eigen, but that's a possibility we could look into in the future. Yeah.
2 quick questions. One, I know I missed, what is the medium and high again?
Yes, I didn't actually explain it, so you didn't miss it. So all of these, the diffusion model that we're using underlying this is essentially a standard marketing model of diffusion known as the BAS model, which is related to an epidemiological model, the SIR models, right? And so medium versus high is a measure of the virality of the product or the piece of information, right? And we used observed empirical values that have been found for these values. And so medium is literally, actually, I wouldn't even call it medium, but I would call it median. It's the median of the empirical values that have been observed. And high is actually the highest empirical value that's been observed. And so this represents how contagious the product or idea is, if you will. So there, in the basic model that we use, there are 2 factors that influence your probability of adoption. One is this contagious rate, this virality rate, and the other is just what we call the coefficient of innovation in the marketing literature, the probability you'll just develop it on your own, right? That you'll just go out and buy the product because you saw an ad and you really liked it. Interestingly enough, from a marketing point of view, we've known from the beginning of marketing research that the virality effect is orders of magnitude more important than the advertising effect, essentially, right? That word of mouth has 10 to 100 times more importance on your decision to adopt a product than anything advertisers do. And so that's often disappointing to the marketing managers I present this results to, but it's pretty well known. Oh, sorry.
The difference between those slopes is significant?
You know, we have 5 data points here, and so I don't really want to make any arguments as to these are squared values or the lines or curve fitting at all. We could explore it in the future with maybe a whole slew of networks where we had some empirical data, but I would hate to make an argument right now.
Yeah. The last question is the seeding fraction, of nodes in the network that you need to seed.
Yeah, it's the budget, basically. Yeah.
sort of analogous to the pathogen introduction rate.
Yeah. Right, exactly. It's very similar to those kind of in many ways. Yeah.
You can use the same high and low or high and medium values from, you say, where does that come from?
Those values come from marketing studies in this particular context. So you would have to readopt these models. You would have to retune these models if you really wanted to look at disease propagation, right? I'm not claiming that these are exact models of those kind of spaces, but these are drawn from the marketing literature, and which we're actually one thing that we're trying to explore is how much of this relates to product diffusion, how much it relates to information diffusion, and that's something we're looking into right now, right? Is how much do those rates change when you move from a product space to just an information space? And somewhat depends upon what's the cost of taking that information into account, right? Like if it's something that really doesn't sit well with your current worldview, it could be very high, right? And if it's, on the other hand, if it's something that's like, oh, now I know who's in the Sweet 16 next weekend, right? That's probably a very low cost, right, of information adoption, right? So that talks about what, how much we have to seed. The next question is who should we seed, right? Which is, of course, the big question. And it turns out that for these 4 networks, which are all the synthetic networks, the answer is really simple. It's dumb, kind of. It's seed the person with the most friends, which is kind of what people have thought about all along. And so it was kind of boring in respect. And if we had gotten that result, I don't think we would have been able to publish a paper. But what we found for Twitter was different, right? And for Twitter, what we found is that degree was very important, but this clustering coefficient notion was also very important, right? And what that led us to believe is that it's not just about people who have lots of friends, but it's about people who have lots of friends whose friends don't know each other, right? And this actually allowed us to quantify how important the degree was to this notion of those friends not knowing each other, right? And this result appeared robust across the level of virality. Of course, with high virality, it's interesting, the importance of clustering coefficient goes up, right, indicating that, in fact, in a higher viral product, that you need to spread wider quicker, basically, in order to maximize your net present value. So why is that solution so important in the Twitter network? So we looked at it a little bit. So this is a visualizations of the Twitter networks. So here you have just the pure degree strategy, and you can see everyone's concentrated in the middle of the network with one little node out here. Here you have just the pure clustering coefficient strategy, and of course you see the periphery of the network because people who are on the periphery don't have any friends who know each other, so they have the lowest possible clustering coefficient. But if you combine these two strategies, what you wind up doing is you're getting individuals who sit at boundary spanning positions in the network, right? But who still have a large impact. They have a large number of friends, I should say. I shouldn't say large impact. So it spreads quickly even from the very first step. And in fact, even these individuals right here, if we looked at it a little bit closer, it's not as obvious in this representation, are not the exact same number of people here. In fact, they're spread out a little bit more widely within that dense hairball that you have at the middle of the network. Our hypothesis is that Twitter, so why didn't this happen in the preferential attachment network, in the small world network, right? Why didn't we see a similar result? And our hypothesis is, and we've seen to show this somewhat true, and we're exploring it more right now, is that the assortativity of real-world social networks is much higher than synthetic social networks. And assortativity is how likely two individuals with the same number of friends are to know each other, right? So it's a measure of how sorted the network is in terms of degree. And in real-world social networks, it seems that it's much more sorted than it is in the synthetic social networks that are out there currently being used to study social phenomenon. And so it's kind of an argument as to why you should maybe use empirical data to actually build your findings in simulation. So we also looked at the Alumni Network that I mentioned briefly. This is so we had a question, like, is this just a sampling phenomenon of Twitter, right? Is it if we had sampled in a different way and we tried a bunch of different sampling methods of the network, obviously we can't get the full multi-billion social relation network and run the simulation on there. We don't quite have the computational power for that. But we wanted to look at different aspects. So we tried that, and it seemed to be pretty robust. But then we stumbled upon one other network that was a nice match for this data, or for this analysis, which was an alumni network from a Midwestern university, and it was a full census of all the connections between individuals in that network. So in some ways you can think of this as literally the total network of people talking about this particular topic, right? And we reran the same same analysis on that network, and we got qualitatively very similar results, where there was a high degree and a low clustering coefficient wound up maximizing the spread through the network. So that made us feel a little bit more robust about these results. So just to quickly move on from this stuff, so the people with lots of friends know other people with lots of friends. They have a higher sortativity, which actually contains social contagion in this space, right? So the way you need to find people with influence is you find people who have lots of friends, but whose friends don't know each other. But as it was mentioned earlier, right, this all assumes that every connection in the network is equal to every other connection in the network, right? That's one of the standard assumptions of this current model and approach. It's obviously not the case. So how can we rip that assumption apart and explore it in a different way? And that's what the next little work is going to be about. So any questions before I move on to trust work? OK. So this is actually a joint work with Sam Sharara, who was a PhD student at the University of Maryland, now at YouTube, and Lise Couture, who is in UMIAX and in the CS department at the University of Maryland. So this was motivated, actually Hassam took my class when I first started teaching here on social network analysis and agent-based modeling, and he thought this would be a great way to model a problem that was vexing him, which was that his friends kept spamming him. And so let me explain it a little bit more. So at this time, Amazon was offering, and the other companies are still doing this, these discounts where if you refer a friend and they buy the same product you just bought, you both get a discount, right? Or something like that. And so, you know, Mary could get this ad for an online bookstore, invite a friend to get 10% off your next purchase. There's no, as you'll notice, there's no disincentive to just not sending it to everybody you know, stated here. Now, there might be a social disincentive, which we'll talk about, but you know, there's no obvious disincentive. And so Mary's like, I'm just going to send that to everybody I know, right? And if one of them adopts it, I get this 10% off, right? And so for some reason, Anne and Janet like it. You know, they like books. But John and Bob, they're illiterate. You know, they don't really read, so they hate the fact they got this piece of spam, right? So over time, what happens is that Anne and Janet trust Mary, and Bob and John don't trust Mary as much, right? They don't trust her judgment to make a decision towards them, right? So John gets an ad from movierental.com, refer a friend and get $10 off your next rental. These are apparently very expensive movie rentals. And John thinks to himself, you know, Bob and Mary are definitely going to be interested. But you know, Anne doesn't like movies. She just likes to stay at home and read books all day, so I'm not going to send it to her, right? And so because John has a little bit better judgment about who to send things to, right, Bob and Mary increase their trust, and there's no effect on the relationship with Anne, right? And if you repeat this process again and again and again, what happens is that everyone starts to trust Mary and, starts to trust John and doesn't trust Mary, right? Is the general idea. And you know, this also has you know, it's not just about John and Mary, it's also about the products that they're sending out, right? So it's also the fact that, you know, the bookstore that Mary is sending out is going to be seen as a spamming bookstore, and the bookstore or in the movie rental place John is sending out is going to be seen as a, you know, as a good place to do business with, right? So we want to encourage people to act like John and not like Mary. How do we do that, right? It's kind of the general idea. So we wanted to capture the fact that, you know, different people have different preferences for different products, right? And that's usually not captured in many of these models. And we modeled the change in trust over time. And finally, we want to be able to design a new strategy that will allow us to take advantage of this knowledge and understanding. So we looked at dig.com, which is a social news website. The way Dig works is I can submit a story that I found online that I really think is interesting. And people can vote it, dig it is what it's called. And if they dig it, then it gets more and more votes and it appears more popular, and eventually it can make it to the front page of Dig, and you know, I get wild acclaim sent to me, right, as a result of that. We looked at both a social network where we had users following other users, so this means I preferentially see your news stories as opposed to random individuals in the network. And we looked at a dig network, which was users voting for stories. And we have 12,000 users in the social network, 1.3 million follow edges. In the dig network, we have 48,000 stories, 2 million dig edges, and we have 6 months of data. One interesting phenomenon that we came up with, so there's been a lot of debate about what's called the echo chamber effect of the social network, right? That essentially, as we continue to build these systems that filter our news for just what our friends want to show us, we start to look more and more like our friends and less like random people out on the street, right? And so we get these kind of balkanization of the internet, or these splitting apart into different pieces. And what we did find some evidence for this, and I don't want to say this is not the point of this paper, so it's not like I would really say that we put an end-all be-all statement on this, but we did find some evidence of this occurring, at least in this particular phenomenon. So what we did was we measured how different two individuals were in terms of the topics that they like to submit stories on, right? So if one person submits stories all on religion and the other person submits stories all on science and never the twain shall meet, right? They're very different from each other, right? And there are 11 different topics they could submit on, so we can measure all sorts of ranges of different distributions of these topics. If they submit on exactly the same topics, say uniform across all the topics, then they're exactly the same in terms of their preferences for each other. So that's what's on the y-axis here. 0 means they're exactly the same. 18 means they're as different as possible as can be in this particular network, right? On the x-axis, we have time, right? And the shading represents the number of stories that they both voted for, right? So the number of times they both voted for the same story, right? And so what we do is we just bin these up, and we count them up. And what you see is that users who started out similar to each other over time started voting for more and more of the same stories. And users who started out very different from each other over time voted for fewer and fewer of the same stories. In fact, seeming to say this echo chamber, the filter bubble, as Eli Parisier likes to call it, really does exist, at least in this particular dig.com data set. Now, there's some arguments on this both ways. Eitan Bakshi, who is a student I worked with at Northwestern, who's now at Facebook, has actually found some evidence the opposite way on Facebook feeds. So I encourage you to dig into this a little bit more if you're actually interested, and I can present you some pointers in that. But at least in our data, we found some evidence that it was happening. So we built a model of trust based upon after we went through this experience of validating that a lot of our assumptions were true in the data. We looked at the fact that we built a model where the probability of user U adopting a recommendation adopting a recommendation from user V is equal to the weight that user V has in user U at time I times the preference that user V has for product C, right? So there's this conjoin of the two things. One way to think of it is there's two reasons why someone might not adopt the recommendation you send them. One is that they don't trust you, right? They simply aren't going to adopt any recommendations you send them. Or two, they don't care about whatever you just talked to them about, right? So they could just not care about science and only be interested in business matters. Or they could not care about sports and only be interested in video games, right? And so we had to capture both of these. This first one captures the trust, and the second one captures their preference for the particular product category. We basically have, yeah.
So that formula, somehow, it's something strange because you have two parameters on the left-hand side, and you have to see.
Yeah.
I don't quite understand how.
So this should be. There actually should be another one. This should be the probability of user U adopting. Sorry, the probability of user V adopting recommendation of user U in category C. Yeah. And really even at time I, but simplified for this particular presentation. Yeah. So you could, so we basically trained the model on the first 4 months of data using a kernel updating rule, and then we evaluated the model on the last 2 months of data, basically. So we assume initially everyone trusts each other. We derive these preferences from the empirical data that we see of what they submitted on, and from that we basically just, if we see a recommendation that gets dug, we increase the trust a little bit. If we see a recommendation that doesn't get dug during the first 4 months, we decrease the trust levels a little bit, and we use that over time to evaluate the model. And then we test it on the 2 months of holdout data. Now, there's one other thing we have to do here. We don't quite know at what level of influence a person's going to decide to adopt a news story, right? Like it might be because people don't show up every day that sometimes they are more likely to adopt things than other times, right? And so we can't control that. So what we can do, though, is we can just vary that threshold for different individuals and then see how many times for a particular threshold, we have a false positive versus a false positive versus a true positive in terms of the overall production. And so that's what this receiver operator characteristic curve is looking at. And it shows that for a lower false positive rate, we get a higher true positive rate than the other two previously established best methods of measuring trust in social networks. So this has all been about how do we actually measure this? How do we engineer people to do things differently in this space is kind of the next question to look about, right? So we conceived of what is currently happening is that successful recommendations are awarded R units. But you could imagine a scenario in which successful recommendations are awarded alpha times R units and unsuccessful recommendations are penalized 1 minus alpha times R units. Now, I'd never claim to take these words and put them on your website as to what you're planning to do for your viral marketing campaign, right? That we're going to penalize our users for sending out recommendations. That would probably not be a good way to get people to adopt. But you could build a system that basically created these incentives without calling them penalties and rewards. And you could, for instance, disproportionately reward people who do a better job of this. In fact, I'm working with some people at Living Social where we're thinking about trying to implement this system within their buy 3, get 1 free system that they have set up, right? So almost every single existing viral marketing strategy assumes alpha equals 1. And which means that there's no reason for the user to be selective, right? They just spam everybody. What happens if you vary this alpha parameter? And what we found, so we again explore we use an age-based model to explore the results. And we assume 2 worlds, one in which every agent knows all of their friends' preferences for products, and one in which they have to learn them based upon what things the people adopt or don't adopt, right? What we find is that in the world in which it's fully observable, if everyone, and you have the alpha equals 1 case, which is the standard viral marketing case, you never get penalized for making a bad recommendation, then what happens is that over time, adoptions drop. And the trust levels, the average trust levels in the network also drop at the same time, right? On the other hand, when you have the alpha equals 0 case, which means that everyone gets penalized and no one gets rewarded, not something I would ever recommend in any situation whatsoever, right? Then adoption stays flat and trust is maintained. Everyone loves each other in the network because no one's ever actually spamming anybody else, right? But the nice thing is kind of the Goldilocks solution, right? Alpha equals 0.5. If you basically weight the number of unsuccessful recommendations with the number of successful recommendations, then you seem to maintain higher levels of adoption and maintain a higher level of trust in the network than other methods that we've looked at, right? So that's in a fully observable case. What about the one in which you don't know whether your friends like movies or not, right? Where you have to learn that from what they do. In this case, we actually have an interesting result. It turns out that for the alpha equals 0.5 case, adoption actually goes up over time, and trust actually gets maintained at an even higher level than the other case. And there's one clear reason why. In this case, we allowed the agents to learn the preferences. But there's 2 reasons, if you remember, why someone might adopt something. One might be that they don't have a preference for it, but the other reason might be that they simply don't trust me. And so what they really learn is they learn the conflation of those 2 properties, right? They learn how much that person trusts me times their preference for that product, right? Which means they do a better job of making recommendations. In this world, they always assume their friends trust them completely, right? Which means that they don't do as good a job of choosing which kind of things to send out, right? It also turns out, just to say, we can move away completely from this idea of actually changing around viral marketing mechanisms to, we can actually identify individuals who have a greater impact on their system, on their social network, by looking at the individuals who are most trusted in that space. one way to think of it is we're essentially inferring the alpha value that that individual places on sending out spam messages, right? We're finding those individuals who do a good job of balancing their recommendations. So what we do is we just simply sum up the amount of trust for those first 4 months of dig data, and then we identify the influentials for the current product category C based upon the users who have the highest preference for submitting on that topic, and then we sort those users based upon their trust levels, right? And what this results in happening is if we then look at the 2 months of holdout data, where we look at how often a person's story got dug in the holdout data, that does a better job of identifying people who are likely to be well voted for, well trusted in the space, than either random individuals in the network or people with the most friends. So again, this high degree notion is not a great way of capturing influence in the network. It turns out that trust does a better job of capturing who is actually the most influential in the space, which shouldn't be too surprising, right? But we actually have some data to back it up. So we can make better predictions about adoption if we take into account these heterogeneous preferences that people have, and we can create better mechanisms to encourage more trust within social networks. Any questions about that?
So just how you computed trust.
Yeah.
Is it based on the training data?
Yeah.
And then you computed trust for each of the nodes.
Right.
And then
we compute it on the dyad level, right? And so then we go to the end of the 4 months of data, and then we just add up the trust, and then we just then we look at the holdout data, right? So we basically, one other little trick it turned out we had to do was we had to figure out which users are most likely to submit on that story, right? So you don't want to identify, even if an individual is well trusted, if they're submitting on an area they don't normally submit on, they don't do well, right? So you do have to kind of take into account what people were trusting them in the past, right? Essentially, this is finding the authorities, right? And then it's finding the well-trusted authorities, right, within that space. Any other questions? Okay. So I'm just going to spend the last 5 minutes. Is that about the? Yeah. Just briefly discussing some work we're doing on urgent diffusion. And so, the general idea is that in most of these cases I've talked about, people spread information at around the same time scale or faster than outside events happening, right? But what happens when outside events are happening just as quickly as information is spreading on the network, right? So you can imagine hurricanes, natural crises, anthrax attacks, things like that could potentially be these scenarios. We looked at 2 different types of data. We have 15,000 Twitter followers we've been following off and on for a couple of years now. And we can also do keyword collections where we just say we want to collect all the keywords. We want to collect all the tweets about Irene, right? And we've looked at 4 different events. The capture of Osama Bin Laden, Hurricane Irene, Hurricane Sandy, and election night 2012. So it's incredible. We were tracking these 15,000 users by chance when Osama bin Laden was captured and killed on May 2nd, 2011. 5,000, almost 5,000 of the 15,000 users tweeted within 48 hours about his death. And they actually tweeted 28,000 times within 48 hours of his death, right? So there were quite a few bits of data. Hurricane Irene, we collected for almost 2 weeks, collected a bunch of different data, and we've looked at both the 15K as well as the overall data. It turns out that this diffusion process looks very different than a standard diffusion process, which I don't want to talk too much about, but essentially there's news events that happen on almost a daily basis, and these cause little new impulses into the system that cause new people to find out about the information and adopt it. We can also geotag these tweets, which I thought might be interesting to some of you, right? So 1% of all tweets have geographical information embedded in them, which doesn't seem like a lot, but when you collect 1 million tweets, it's a decent number of tweets that you have that have geotagged in them, right? So this is all the Hurricane Irene geotag tweets. One interesting thing is Antarctica tweeted about Hurricane Irene, but then the other interesting aspect is this little trail heading up the east coast of the United States, right? which seems to exactly match the hurricane's path. And so this caused us a little bit of question as to why are people tweeting about Hurricane Irene off the eastern coast, unless, are they following the hurricane? It turns out there's actually a weather service that spoofs the exact coordinates of the hurricane and tweets the barometric pressure of the hurricane at those coordinates, pretends to be the hurricane tweeting in a way. I mean, it doesn't really, it's not faking it out. It's like saying, here's the hurricane. But buried in the metadata, which no one sees, is that exact geolocation tag, right? And so it's kind of bizarre that they do that, because it's only for people like us who are ever going to find that information. Here's Hurricane Sandy. It actually looks very different than even Hurricane Irene. Hurricane Irene had a bunch of information happening right at the beginning and then seemed to level off over time. Hurricane Sandy had actually more tweets occurring as the events were unfolding in New York than actually happened during landfall, right? So it's kind of an interesting balance of what's going on and provides a nice set of data to look at. Election, we have 10 million tweets. This is our largest data collection ever. From a 24-hour period, we have about 40 million tweets in the total corpus when we extend it out to another week. We've looked at a number of different things, but one of the most interesting is that these are the state by state for the top 4 electoral vote battleground states. And you see these peaks happening at 7, 8 o'clock, 7:30. Anyone know why they'd be happening then? Why the jumps? It's when the polls close, right? As soon as the polls close, tweet volume shoots through the roof in terms of each of these states and talking about them, right? Mainly because it's the first time the news agencies can start speculating about it. I do want to mention briefly on a side and kind of related to that, one thing I'm starting to look into that I thought might be interesting for some of you is relating space to social media. So how does where people are talking about things affect what they're tweeting about, and how does that information exchange happen? And there's been some previous work in this space, similar to the hurricane graph I showed you, looking at things like predicting the path of typhoons across Japan based upon people tweeting about it and without any knowledge of the path. And in fact, they get a very good match in many of these cases to the path that actually took by just looking at the volume of Twitter and what's going on there.
Are these independent?
What?
Are these independent events? I mean, don't people tweet because...
They tweet because there's a typhoon.
And because of this is its path.
Yeah. So, but what they're showing is that where the tweets are coming from can determine the path, right? So the closer you are to the path, the more likely you are to tweet about it, and which maybe that makes perfect sense. Yeah. But it also means that we can actually use some of this data to detect things that maybe are less obvious than typhoons are moving across there, right? Potentially. They've also looked at it in floods and fires. So this is, I believe this is North Dakota, right, in Minnesota, in that area. And they've looked at the spreads of different floods occurring along this and how people have responded and denoted what's going on. And then using that to try and infer information about the extent of flooding and things like that going on in these spaces. Yeah. So a lot of different things along these lines. What I would actually like to do is take a contained geographical location and start to collect as much geolocated data as I can from social media to build a model of human activity, all the things that are occurring in that space, in that system. And so that's something I've started working on and we've started looking at. And so not just looking geolocated tweets, but also looking at ambient geography, which is mentions of geographical locations in social media data. Like, people might not geotag their tweet, but they might say, I'm standing near Annapolis, right? Or something like that in their tweet. And so can we use all that information together to kind of build a larger scale model of what's going on? Finally, as I mentioned, some of the exact same techniques in the last slide are also useful for understanding environmental impacts as well, right? And so we used ABM and GIS to understand suburban sprawl. What's nice is means we can empirically ground the model with full heterogeneity. So in this particular case, this is Washtenaw County and some of the areas in southeastern Michigan where we were based. And we drew data from the Detroit area survey about why people would decide to live where. And then we built a model from that data and we made predictions about what areas would be developed and what the impact of different policies like zone land use would be on those spaces. And we had a number of different publications in that space that talked about the looks of those spaces. Actually, I lied. I have one more slide because as part of that, I got invited to attend what was called COMSES, which was the Network for Computational Modeling for Socio-Ecological Science, which was an NSF-funded network of scientists based out of Arizona State University. And I'm now actually on the interim board. They're trying to transition it off the, oh gosh, I'm trying to remember the name of the RCN funding to some more ongoing funding projects, and we're working on that right now. So I thought that group I just wanted to mention because I thought they might share a lot of similarities and interests with SESYNC. Part of what they do is they maintain a website called OpenABM that's a resource for researchers and educators interested in teaching computational modeling for this space. So if that, thanks, sorry for running a few minutes over there. But there's my email address if you need more, the center's website, and that's our research paper series that basically all the papers I've talked about today are up on. So thank you very much.